All right, in this video, we're going to see the similarities between converging lenses and mirrors and some things that are always true for them. So I'm going to start with this problem right here. All right, I've drawn a converging or convex lens here, an object over here, there's the focus, and there's 2F. And I mentioned briefly that 2F and F are going to be turning points, and that's kind of what we're going to be talking about today. So right now, the object is beyond 2F. All right, away from the lens. I'm going to quickly draw the ray diagram for it. So a ray that goes in parallel gets to the center line of the lens and goes down through the focus, like so. And then the second ray that I draw always goes from the top of the object through the center, so like so. And where they meet is the image, so the image is over here. And we're going to write down that the image is it's inverted, shrunk, and real. And one last thing we're talking about is where it's located. And see how it's between the focus and 2F. It's beyond F and 2F. And there's going to be a pattern. Whenever the object is beyond 2F, whether it's here or here or here or here, the image is always going to be between F and 2F, and it's going to be inverted, shrunk, and real. And we want to know what happens when the object gets to each of these turning points. And it turns out that no matter what my convex lens looks like, these rules are always going to be the same. Now I can do it with math as well. So for the math, let's take a look at this. We're going to say F, I'm just going to make up some numbers. Let's say F is 2, 2F is 4. So the distance of the object has to be bigger than 2F. So let's pick a number. Let's make it, say, 8. And let's make the size of the object 2, because it's too high here. All right. Now, when I do the math, 1 over dO plus 1 over di is 1 over F. All right. 1 over 8 plus 1 over di is equal to 1 over 2. So 1 over di is 1/2 minus 1/8. It's going to be 4/8 minus 1/8 is 3/8. So di is going to be 8/3, which ends up being 2.6 repeating. Now you'll notice that's between F and 2F, because F was 2 and 2F is 4, so it's between the two, just like we see on here. And if I do the size equation, size of the image over size of the object is minus di over dO. Okay, SI is what we're looking for, over 2, because it is equal to minus 8/3 over dO was 8. And I get SI is minus 2/3. So the negative means inverted. And it shrunk. Okay, because it's only 2/3 high, whereas the object was 2. Now, I found a website that illustrates this really well. All right, and I'll put a link to it. But here is my object. Okay, it's a candle. And right now it's beyond 2F. And you'll see that no matter where I move it beyond 2F, the image is between F and 2F. It's real because the rays of light get there, and it's inverted and it shrunk. All right. And if I move this to exactly 2f, remember that's one of the turning points, and I've got to get it exactly there if we can. There we go. Okay, it's right on 2f. Because the focal length is 20, the object is at 40. Well, look what happens now. The image is exactly at 40, exactly at 2f. It's inverted, and it's the same height. So out here, it's real, inverted, and small. But when I get to 2f, it's real, inverted, and the same height. All right, now, if I continue inward between f and 2f, I still get an inverted image, but now the image is beyond 2f. So if I'm out here past 2f, the image is between f and 2f. If I'm at 2f, it's at 2f. And then if I bring it inside f and 2f, it goes beyond f and 2f, and it's magnified, still real and upside down. I'm going to continue onward, and I'm going to get right to the focus here. And again, I want to get the number exact if I can. There it is. All right, focal distance is 20, and it's right at 20. And here it's saying the image distance is an infinity, but basically it means there's no image because these two lines end up being parallel. They will never meet. So when the object is right at f, I have no image. And now watch what happens when I move it inside of f. Now, if I'm inside of f, that's when you get this magnified virtual upright image. So what the image looks like depends on where the object is. If it's beyond 2f, it's small and inverted. If it's at 2f, it's the same size and inverted. If it's between f and 2f, it's larger and inverted. At f, there's nothing. And inside of f, the image is virtual and upright and bigger. Now, let's take a look at a mirror. Actually, let's look at diverging lenses. Diverging lenses are simpler in that, let's make the image bigger. In that, no matter where I put my object, okay, here's my image is right side up, and it's small, and it's virtual. Okay, no matter where I put it, I get the same thing. So they can only make small, virtual, and upright images. So diverging, small, and upright. Converging, you have lots of different ones. Now let's look at a mirror. This is a concave mirror, okay? And it's a converging, and you'll see the same relationships. If I'm beyond 2f, I get a small and inverted image between f and 2f. When I'm right at 2f, okay, the image is at 2f, and it's the same size. If I keep moving inside, now I get the magnified image. If I go right to f, try to get there exactly. There we go. I get no image at all because the lines are parallel. They never connect. And then inside of f is when I get the large virtual upright image. So I've made up this chart that puts all of this together, and you can kind of memorize this. It's not that difficult, and it makes things a little bit quicker. Or just like I did at the beginning of the video, you can always draw a sketch or do the math to figure this out. Okay, but if I have a converging lens or a converging mirror, which is convex lenses and concave mirrors, if I'm beyond 2f, I get an inverted, shrunk, and real image located between f and 2f. If I'm at f, no image gets formed. If I have a diverging lens or mirror, and so I flipped around, I have concave lenses and convex mirrors, no matter where the object is, I always get an upright, shrunk, and virtual image that's behind the lens or the mirror.